Now we're going to talk about model specification. Remember, for the purpose of model specification, you need to understand what kind of error in specification there are covered in the curriculum, and more importantly, what does it do, what effect it has, what effect does the misspecification have on the outcome, on the output of the regression result. So happy learning. Model specification is two types. One is selection of explanatory variables, meaning choosing the right X variables. For doing that, the analyst has to have a firm understanding of the economics of the dependent variable, the Y variable. What are the sound economic influences that should be included in the model? That is a key question. The second issue pertains to transformation of variables. Now, if a model is misspecified, then it creates problems with respect to hypothesis testing, creates problems with reliability of the slope coefficients. The slope coefficient may be biased/inconsistent. Now, there are four types of misspecification. The first one is where important X variables are excluded, not included. And so they should have been included but omitted. The second one is there is improper transformation of the variable where transformation was needed but was not conducted. We'll see an example in a little bit. The variables were not scaled properly. For example, if I was to compare net income of two technology companies with different sizes, one is a very big tech company, another one is a small company. Well, by looking at raw data for net income, that comparison is meaningless. Instead, I may want to use a common size element or common size statement comparison. So, for example, I may want to compare operating margin or net income, net profit margin to make that comparison. So, scaling of data is important. And then finally, data being pooled improperly. When you have structural shift in the economy and you're collecting time series data that extends in two separate regimes, then what ends up happening is the underlying relationship between Y and X variables may have shifted, may have changed. Remember, that relationship is captured by what? By the estimated slope coefficient, the betas. Now, if the relationship has shifted, the betas would change. But you, not being cognizant of it, not being aware of it, chose a long sample. Now, what will end up happening is once you feed it to your software package will estimate a coefficient that is appeasing to both data sets, both structural periods. And when you use that model to generate forecasts, well, you're going to give lousy forecasts. Ideally, you want more recent data because that data is reflective of expectations going forward. So ideally, you want your more recent sampling period as opposed to longer period, which includes a different structural regime. So data is being pooled improperly being a concern. Now, a key takeaway here is the impact of these actions on our regression output. So omission of variables can lead to bias and inconsistent regression parameters or coefficients. So we are talking about bias and inconsistent coefficient or betas. May lead to serial correlation or heteroscedasticity as well. Inappropriate transformation leads to what? Heteroscedasticity. Inappropriate scaling leads to heteroscedasticity/multicollinearity. And then finally, incorrect pooling. Now remember, this is time series. Whenever you see time series, you're concerned about serial correlation. So that is the effect for improper pooling of data. Now let's look at an example to see how these misspecifications can manifest in a model. So what we are going to do is to take an actual example, which is based on Wang and Su, published in FAJ, which is a CFA Institute publication. And obviously the model that was published was not misspecified. What we are going to do is to show you if the researchers were not good quant analysts or did not pass level 2 of the CFA exam, what kind of mistakes maybe they made. So these are the 4 X variables that were included. Remember, the Y variable is Chinese stock returns. They specified a portfolio, and this data was collected monthly, and they have 4x variables that they included. And so here is your model. All right, now let's see what kind of misspecifications could have occurred. We'll look at all 4 types. The first one is omission of the variable. So instead of we leave out natural log of market cap, right? And one of the key concerns here, when you leave out an omitted variable, and if that is correlated. Now I'm saying correlated, I'm not saying highly correlated. If it is highly correlated, that is multicollinearity, that is a problem, and there is a solution to it, which we'll see later on. Right now, we are only talking about correlated. So market cap, say for example, is behaving kind of similarly as, say for example, free float. Well, if that is the case, if large companies have bigger float, if that is the case, for example, then what ends up happening is the impact that should have been captured by market cap is now being captured, at least to some extent, at least partially, by free float variable. So the coefficient for free float includes credit that should have been assigned to the missing variable. And so obviously that coefficient is becoming biased. So that is misspecification number 1. The second misspecification is inappropriate variable form. Remember, the reason researchers used log of market cap and not just market cap in dollars or whatever, and that is because the relationship between returns and market cap is quadratic. So what you want to do is to take natural log of market cap to make it linear. So you know, it's kind of like if you were to do a compounding, and you look at the graph of compounding, calculating future value, and you see a quadratic relationship. As time goes by, the future value grows exponentially, and that is the nature of time value of money. Well, same principle, market cap will grow with return over time, exponential relationship. Well, we want to convert it into a linear relationship. To make it happen, we need to take natural log of market cap. All right, so that is the second misspecification. If you don't take the natural log, you would have made a mistake trying to fit in a quadratic model, quadratic relationship in a linear model. Not going to do a good job of it, not going to generate good forecast. The third misspecification is inappropriate scaling. Now, one of the variables included is free float. If I just include raw data, meaning a raw number of shares in a free float that is available in the market as free float, well, that would be unscaled data. Instead of that, I want to do a proportion, percentage of free float relative to outstanding number of shares. That would be more appropriate metric to use in the regression. Finally, the last one. What if the data set that they have used, in our example, they have basically used data from 96 to 2002. What if the data from 96 to 99 is structurally very different? The relationships between X and Y has changed in more recent times from 2000 to 2002. Well, by combining them, you are essentially trying to appease to both data sets. Your coefficients are going to be garbage and not going to generate a good forecast for 2003 and so forth. So that is 4 misspecifications. All right, let's move on to the regression assumptions. We already went through the list of assumptions, and we said at that time there are 3 specific assumptions that we're going to see in a little extra depth. Here we go. So for each of these 3 assumptions, we need to know what it is, what is the impact on the regression output, and that is actually one of the important elements of understanding these violations. What are the mechanisms to detect these violations? And then finally, what to correct for it. So correction is A-okay in the sense that that is just memorizing some labels, and we'll see that when we get there. So right now, our focus is on effect it has on statistical inference and the detection of those violations. Now, the first violation is heteroscedasticity. It is a mouthful. Heteroskedasticity, by the way, skedasticity is a mathematical term and it really refers to variance. So volatility, skedasticity is same as volatility or variance, all right? Hetero means fluctuating. Homo means constant. So homoskedasticity means constant variance. Heteroskedasticity means fluctuating variance. It is not constant. Now, heteroskedasticity is a violation. Remember, one of the assumptions of multiple regression was the volatility, the variance of residual is constant, or residuals distribution is homoskedastic. That is the appropriate term. Once again, residual distribution is homoskedastic. Now, if the residual distribution is heteroskedastic, when its volatility changes, then we need to ask ourselves, is this heteroskedasticity conditional or unconditional? Unconditional heteroskedasticity, just like unconditional love, is okay, no problem. However, if the heteroskedasticity is of the conditional kind, if it is conditional heteroskedasticity, then there is a problem. So what is this conditional heteroskedasticity? Conditional heteroskedasticity says that the volatility, the fluctuation in volatility of the residual is systematically related to one or more X variable. It is conditioned upon the values of these X variables, hence the label conditional. So conditional heteroskedasticity tells you that the change in volatility, the fluctuation in volatility of the residual is systematically related to one or more X variables. Okay? And if that is the case, then there is a problem. Now, what is the problem? Remember again, heteroskedasticity is for what? For the residuals. And because it is concerning the residuals, it affects what? The standard error. So in our T statistic, the standard error is unreliable. The slope coefficient is still okay. They are still consistent, unbiased. That is what I mean by not affected. So the betas are okay. They're still consistent, they're still unbiased, but the standard error is unreliable. In the case of financial data, all right, so in general, we say that the presence of conditional heteroskedasticity makes the standard error unreliable. However, for financial data, we can kind of be a little more precise. And again, it is sort of not always true statement, but in general, financial data, what we normally find is that the standard errors are understated, meaning it is too low. If standard errors are too low, then the T statistic is too high, and therefore you end up committing type 1 errors. But again, that is only as a unique observation for financial data. All right, so here is a graphical representation, again in a two-dimensional space, because that is the limit of my exposition ability. And so I have the X and Y, and then the scatter plot indicates the errors, meaning the distance from the linear equation, the red line, that is my residual. And each of these distances represent a different residual. And as you can see, the residuals are more compact, low volatility when X values are low, but the volatility increases, they're more spread out when X values are high. So that is an example of a conditional heteroskedasticity, which you can see visually. Now, not all data is as obvious as what we just saw, and so we need a more formal test of checking for conditional heteroskedasticity, and that more formal test is the Broch-Pagan test. Now, the Broch-Pagan test is conducted by first regressing the squared residuals. So think of it, you have this. So you have this, think of it as Excel spreadsheet. you have y variables x1, x2, x3, and you have these columns, all right, in a spreadsheet, all these observations. And there are three variables, three x variables, or three independent variables in your model, right? So once you run your regression and you get your beta 1 hat, beta 2 hat, and beta 3 hat, and then also beta naught, and then you plug in the values of x1, x2, x3, and you get your estimated y value. And then finally, you arrive at the residual, so y minus y hat will give you the residual, the error. So for each observation, there is a residual that you can calculate after you fit the model and after you estimate the value of y. So now this column of residuals, what I do is next square them. So residuals, by the way, when you add them together under OLS, it'll always add up to 0. So there are some positive, some negative. When you add them together, it's 0, so that the mean is also 0. And remember, one of the assumptions of multiple regression was expected value of the residual was 0, or the mean is 0. All right. So we don't want them to add to 0, so that's why we square it. So all your negatives also become positive. So you square the residual, that becomes the next column. Now you're running a new regression, and where you have the residual square as your y variable, and then you still have the same x1, x2, x3. Now, if your residuals were truly random errors, they are white noise or whatever you call it. If they are truly random errors, then the model that you're estimating will have r square close to 0. Your x variable should not be explaining the variation in these squared residuals. So your r square should be close to 0. But if your data has conditional heteroscedasticity, then your r square may be high. You multiply n times that r square, and that r square, be careful, in decimal, not in percentage. So that r square multiplied by n being the number of observation, that is a chi-square test with k degree of freedom, all right? K being the number of x variables in your model. So that is your Broch-Pagan statistic. And if your Broch-Pagan statistic chi-square is greater than the critical chi-square, then you reject your null and conclude conditional heteroscedasticity. So your null hypothesis is no conditional heteroscedasticity. When your chi-square that you calculate is higher than the critical value, then you're going to say we have problem with conditional heteroscedasticity. All right. So let's do a quick example. You've been studying 5 years of monthly returns. So 5 years of monthly returns means n is equal to 60. And you're basically having the funds return as your y variable. You regression the funds return on S&P 500 index. That's your x variable. So there's only one x variable, so k is equal to 1. And your regression output does not seem to be correct. The standard deviation return beta don't seem to support the risk profile. So what you do is you visually examine your residuals and plot them in relation to the independent variable, the x variable. What you want to do, what you want to see is that there should not be systematic pattern here. The noise, the residual, should be randomly distributed around the x variable. Well, what I see here is the volatility is low at low values of independent variable and high at high values of independent variable. I mean, I could have seen volatility high at low values and low at high values. Still, that would be called conditional heteroscedasticity. Still, it would be a problem. So that is just a visual quick examination. because I'm not convinced that I have my data is clean. I'm not convinced that I don't have conditional heteroscedasticity. I run a formal test. So, for doing the formal test, I need the R square. Remember, R square is where I'm regressing the squared residuals onto the original independent variables. And when I do that, I see my R square is 8%. And so my Broch-Pagan statistic chi-square is equal to n, which is 60 times 0.08. Remember, instead of 8%, use the decimal form. All right? And this will be equal to 4.80. Now compare it to the critical value from the chi-square table. Again, if you're going to be tested on it, partial chi-square table will be provided. So the level of significance is 5%, and they have given you the partial table. How many degrees of freedom? Remember, degrees of freedom is k, which is equal to 1 in this example. So 1 degree of freedom, the critical value is 3.841. Compare it to 4.8. And we know that the 4.8 is obviously greater than 3.841. So we reject the null, and you have a problem with conditional heteroscedasticity. Now, the second assumption is the residuals don't have serial correlation. Again, it pertains to residuals or errors and affects what? The standard error. Notice the slope coefficient is still okay, consistent, unbiased. Okay, so the beta is okay. The standard error is problem. When standard error is a problem, that means what? Your hypothesis testing is a problem. Your t-test is a problem. Your f-test is a problem. So for serial correlation, there are two kinds. One is there is positive or negative serial correlation. What is positive serial correlation? Positive serial correlation says that if, for example, residual in period I is positive, then residual in period I plus 1, the probability of that residual being positive is greater than 50%. Remember, if it is purely random, then the probability of the next period residual should be 50-50, positive or negative. But if it is positive serial correlation, it is more likely to have the same sign as the residual before it. It doesn't mean 100% likelihood the next period residual will be positive. Remember, at the end of the day, the sum of residual is 0. Still, it will work. But at some point, it'll flip, and there will be a series of negatives, and then it'll flip, and then it'll have a series of positive, and so forth. So if I were to plot it, positive serial correlation would look something like this. And this is, again, a very dramatic illustration, but that is a very dramatic illustration of what I call as positive serial correlation. Negative serial correlation would be, the signs are kind of alternating. It doesn't always happen that way because this is all a game of probability. If it is purely random, then the probability of next period sign is 50-50. But in a negative serial correlation, the probability of with an opposite sign is greater than 50%. That is negative serial correlation. All right. Now, when it is positive serial correlation, then the standard error is too low, which leads to too high a t-value, and you get type 1 error. If it is negative serial correlation, you get to type 2 errors. Obviously, all hypothesis testing, if your standard error is affected, it also affects your f-test. All right. Now, how do you detect serial correlation? One is simply a scatter plot, like I just showed you. If it is, but that is only for a very dramatic serial correlation. So positive and negative. But as I said, again, only for very dramatic. We need a more formal mechanism to test for serial correlation, that is Durbin-Watson statistic, but it only is capable of covering serial correlation at one lag. So say, for example, you're dealing with monthly observation, then you can use Durbin-Watson to see if the residual in March is affected by residual in February or residual in April, but there's only one lag. But what if the residual in March is affected by residual in January, 2 lags? Well, that is not something Durbin-Watson is capable of unearthing. So more generic, more powerful and more general test is the Broch-Godfrey test, the BG test. And it allows for testing at several lags, as many as you want to specify. Under the BG test, what you do is you use the residuals as your dependent variable, is your y variable. And notice I have my x's this should be, so I have my x's as my independent variable, the original raw data, same x values here. And instead of betas, I have a's, because I recognize obviously the slope coefficient in this model is going to be different than the slope coefficient I got when I ran with actual dependent variable. So, but that is not something of my concern. My real concern is, is these terms. Here I have 2 lags being included in my model because I'm checking for serial correlation at 2 lags. So I want to see this, lag 1 and lag 2 coefficients, are they statistically significantly different from 0? So we run an F test with, remember, F test has 2 degrees of freedom, the numerator and denominator. P degrees of freedom in the numerator and n minus p minus k minus 1 degrees of freedom in the denominator. Now P, what is P? P is the number of lags I'm testing. In this example, I have 2 lags that I'm testing. And so the null hypothesis, that is the key. You're not going to run an actual F test, but recognize qualitatively at least what this test is doing. So your null under the Broch-Godfrey test is there is no serial correlation. So you have to reject the null. And the F has to be greater than critical F value for you to reject the null hypothesis of no serial correlation. So if most statistical packages provide that F value, your job is to say, okay, it is greater than critical F value from the table, and therefore I'm concluding there is serial correlation. Now, the Broch-Godfrey does not specify positive or negative. Durbin-Watson does, but remember, we are not too worried about that test, at least as far as the exam is concerned. So all we have to do is to Broch-Godfrey allows for testing of serial correlation of multiple lags, and it is an F test with P, comma, n minus P minus K minus 1 degrees of freedom. Now, how do you correct for serial correlation / conditional heteroscedasticity? Remember, both these pertain to the residual. Heteroscedasticity of what? Of residual. Serial correlation of what? Residual. Because they both pertain to residual, it affects what? The standard errors. So if I want to correct for those issues, those violations, then I fix my standard error. And so I use what is called as robust standard error. Earlier I mentioned that it's the correction part is easy, you just need to memorize. This is what I meant, memorizing the name Newey West for serial correlation and White corrected for heteroscedasticity. So this is just a label. Again, you're not going to be able to the actual mechanics of this correction is beyond the scope of the curriculum. So you just have to remember the label assigned to different corrected standard errors relative to the violation that you are trying to correct for. All right, the last one, multicollinearity. Multicollinearity occurs when 2 or more X variables are highly correlated. So I need to emphasize the word highly. Okay, very important. So some correlation is expected in any 2 variable, doesn't matter. But highly correlated, that's when there's a concern. In fact, when you go back to your list of assumptions, you'll see that X variables are linearly related, meaning they're perfect correlation, either perfect -1 or perfect +1. But even if they're highly correlated, then there is a problem. Now, what is highly correlated? That is not covered in the curriculum. In fact, there is no standard definition. But in general, we say that when the correlation is greater than positive or negative, greater than positive 0.7 or less than negative 0.7. But that only works for a pair. What if x1 is correlated with a linear combination of x2 and x3? That is also a problem under multicollinearity. So that simple correlation is not sufficient to unearth the concept of multicollinearity. We'll see a formal test in a second. What does multicollinearity do? Remember, multicollinearity is not about residuals anymore. It is about the X variables or the independent variables. So now your X variables are affected. So what does it do? It also makes betas unreliable. All right? So your slope coefficient is no longer reliable. Now, my favorite example to explain multicollinearity is, say, for example, your car breaks down. You pull over on the side of the road, you call up some of your trusted friends to come and help you. You don't want to pay for a tow truck. There is a service station close by, and you want your friends to just push you down to the service station, quarter of a mile down the road. And so your friends show up and they're all helping you push your car. It's and the car is moving in the right direction. Similar to when you see a model, you see that the model is working. Your coefficients are statistically significant, or at least, sorry, your R square is decent. Your F statistic is good. So your F statistic for the full model, saying all variables are 0 versus at least one of the variable is positive or significant. That F test is showing that the model works. But you are going to be hard pressed to identify amongst the 4 friends that you have invited to help you which one is actually doing the job versus which one is faking it. So you could be having somebody just pushing it, faking to push the car. So it's very difficult to precisely identify the credit to be assigned. Same thing happens when your variables are highly correlated. They are behaving very similarly. It's hard to tell who is actually contributing to the explanatory power of the model and who is just along for the ride. So that is a concern for multicollinearity, and therefore it increases the chance of type 2 error, meaning the friend that was actually doing the job may appear to be less valuable to you because they are sharing the credit with the laggards. So that is what I call as type 2 error. You think that the variable is not as statistically significant. Now, detection of multicollinearity, one way is where you look at an overall model and it has a good F statistic, meaning the model is model is working collectively, but individual slope coefficients are not statistically significant. Well, that tells you that they are sharing the credit. Another approach is we will see a VIF test, which in a little bit, but the correction for multicollinearity is removing one or more X variables. There are actually 3 possible approaches. We'll get into them next. So first, let's look at a quick example of detection of multicollinearity where we have a disconnection between the F test and the T test. Now the p-value, we went over this, we compare it to the level of significance alpha. Let's suppose alpha is 5%. The p-value is associated with the 3 independent variable. You will see p-value is greater than 0.05 or 5%. In all cases, the p-value for variable 1 is 0.15, that is greater than 5% or 0.05. Same thing for variable 2 and variable 3. However, the f-stat, that is less than 5%. It is less than 0.05. It's actually less than 1%. So it says that the model itself collectively is doing a good job of explaining the variation in y, but we can't tell which variable is doing the job. All three appear to be lousy, at least based on the regression output, based on our understanding of statistics. So this is a classic illustration of multicollinearity. More appropriately, more powerfully, we have a variance inflation factor test. So what is VIF? So think of it as I will run a regression. So say, for example, I have three variables, x1, x2, x3. So I'll take x2 on the side and make that my dependent variable, and I'll have two independent variable. Basically, I'm running a standard multiple regression OLS estimation process. And what I find is the R square from it is, let's say, 10% from that regression. Now notice, x1 and x3 collectively is explaining 10% of variation in x2. Higher the R square, higher the implicit relationship between x2 and the other two variables. These are all three of them are independent variables. You want low R square. All right, coming back. So for j, variable j, I take 1 divided by 1 minus R square, where that variable j is the dependent variable. That is your y variable. So when you keep one variable as a y, the rest of them as x, run a regression, get your R square for that regression, and that is used in this formula. So you have 1 divided by 1 minus R square. As I said, if R square is 10%, then it will become 1 divided by 1 minus 0.10, or 1 divided by 0.90. And that is, 1.11. All right, so what does these values of VIF mean? If R square is 0, right? If there is no relationship at all, then the lowest value that VIF can take is 1 divided by 1 minus 0, or 1. So if it is 1, then there is no evidence of multicollinearity at all. But even if it is above 1, doesn't necessarily mean. If it is greater than 5, that means what? There is a warning sign. You need to be cognizant of the fact that there is potential multicollinearity. Further investigation. If it is greater than 10, but that occurs when R square is 90%. So if I were to put 1 divided by 1 minus 0.90, you get 1 divided by 0.10, or 10. So when R square is greater than 90%, then you get VIF of greater than 10. That is a serious problem with multicollinearity. What are the solutions? We already went through dropping one or more regression variables, the ones that are correlated. Yeah, maybe you drop them from your model because they are highly correlated. Maybe there is no value to having two variables saying the same story. So that is one approach. The second one is use a different proxy for the variable. For example, in your model, if you are trying to include a variable that captures the liquidity of a specific security, let's say it's a bond and you're concerned about liquidity risk premium, explaining the yield on a bond. So you have a liquidity metric as one of your X variable, and let's say you use free float, again properly scaled as a percentage, as one of your variable, and you find that that variable is highly correlated with something else in your model. So instead of using free float, maybe you use bid-ask spread as a metric to denote liquidity risk. So use a different proxy perhaps to remove this multicollinearity concerns, or finally increasing the sample size, which basically makes it statistically more robust.
So those are the mechanisms by which you detect multicollinearity.
Okay, so that was a lot of learning and a little intimidating, but don't get stressed. Continue your journey. You have time to review it later on as well.